In this video, we're going to try to solve this given initial value problem by finding an appropriate integrating factor. Now, this problem is an example of how do we make a differential equation an exact DE by multiplying an integrating factor. Now, the first thing we're going to do is to test this differential equation whether or not this is an exact one. And if it's an exact one, we'll find a solution right away. And if it's not exact, we'll try to make it exact by finding an integrating factor and multiplying that to our original differential equation if it's possible. And later, we'll try to find a solution to that. Now, what we need to know about an exact differential equation is that for a DE or differential equation to be called exact, this equation here should be satisfied. My is equal to nx, where your my is the partial derivative of m with respect to y and your nx is the partial derivative of n with respect to x. Now take note that both of your m and n are functions of x and y. Now to identify m and n, we should rewrite the differential equation in this form. M dx plus n dy is equal to 0. Now rewriting this, we just subtract y plus xy dy to both sides of the equation so that we're left with 0 in our right hand side expression of our differential equation. Now rewriting, we have our m as x squared plus y squared minus 3 and our n as negative quantity y plus xy. Now taking the partial derivative of m with respect to y, we'll treat the x here as constant and we'll treat the y as variable. So the derivative of x squared minus 3 is just 0 since this is constant, since we're differentiating with respect to y. And we'll take the derivative of y squared, we have 2y. That's why our my is equal to 2y. Now our n is negative quantity y plus xy or negative y minus xy. So in taking the partial derivative of n with respect to x, we'll treat y here as constant and we'll treat the x as the variable. So meaning the derivative of y here is just 0. So we'll take the derivative of negative xy here with respect to x so that our nx is negative y. So as you can notice here, my is equal to 2y and nx is equal to negative y, meaning they don't have the same values, which means our differential equation is not exact. Now let's make this an exact differential equation by finding our integrating factor mu of x is equal to e to the integral of r of x dx, where your r of x is equal to my minus nx over n. This is your my, nx, and n. And let's substitute and plug that into our equation or formula. 2y minus negative y is just 3y, and our n is negative quantity y plus xy, factoring out the y and then canceling out y over y because this is just 1. So we're left with negative 3 over x plus 1 as our r of x. And let's plug that in here in our formula for our integrating factor mu of x. And then integrating this, moving this out the integral because this is just constant, the negative 3, and integrate 1 over x plus 1 dx, we have e to the negative 3 ln of x plus 1. And according to the properties of logarithm, the power rule, we can move this negative 3 up here and make this the exponent of x plus 1. And then furthermore, we can simplify this and we can cancel e and ln here so that we're left with x plus 1 to the negative 3 as our integrating factor. Now, after we found our integrating factor, let's multiply that to our original differential equation, x plus 1 to the negative 3. This is our integrating factor, and we're multiplying that to our dE. So that's why. And also, we can simplify this further so that we will have our new m here as this one and our new n here as this one. So our new m is this, and we're taking the partial derivative of this with respect to y. We can treat this as constant, so meaning this must be left unchanged, and then we're taking the derivative of this expression here with respect to y. That's why we're left with 2y here, 2y times x plus 1 to the negative 3. And our new n here is negative y quantity x plus 1 to the negative 2. So let's take the partial derivative of n with respect to x here, so this y here is just constant, so we have negative y times the, bring this down here, negative 2, and then subtract 1 from negative 2, we have negative 3. That's if we can notice here that our my is equal to our nx. That's why we can conclude that we already made this differential equation an exact differential equation after multiplying the integrating factor to our equation. Now, after finding out that our differential equation is exact, we then find a solution to our differential equation. Now, to find the solution of our differential equation, the f of xy will try to go back to the form mdx plus ndy is equal to 0. But instead of writing m and n, we'll write the partial derivative of f with respect to x as our new m, and the partial derivative of f with respect to y as the n. It's just the same form mdx plus ndy is equal to 0, only we're dealing with the partial derivatives of f with respect to x and y respectively. Now, to find the solution f of xy, take note also here that our partial derivative of our solution f with respect to x can be denoted as fx, and the partial derivative of the solution f with respect to y can also be denoted as fy. Now, to find a solution of f of xy, we can integrate either fx here with respect to x, or we can integrate this fy here with respect to y. Either case will work, but we'll find which case is better and is easier to integrate, since here we can see that fx, or this expression, has factors x squared plus y squared minus 3 and x plus 1 to the negative 3, where their inside terms contain the variable x. Then we'd find this harder to integrate. Well, if we do this integration here below, if we integrate fy instead with respect to y, since our variable is y, and we can simply hold this x plus 1 to the negative 2 as constant, so we'll only deal with integrating the y. So this one is easier, so we'll try to integrate fy with respect to y here. Now we'll use this formula, integrating fy with respect to y. We have this solution here, since this is our new n. We're moving this out since this is just constant, because we're treating x here as constant because we're differentiating or integrating with respect to y. So we're moving this out, the integral, negative x plus 1 to the negative 2, and we're integrating y dy. The integral of y dy is just y squared over 2. And also, after taking the integral, we should account for the function g of x, because we should also and always account for the constant. But since we're differentiating or integrating with respect to y, then we have our function g of x here as constant. Any function of x is a constant because we integrated with respect to y. Now after that, we'll take the partial derivative of f with respect to x. Why do we take this? Why are we finding the differential or derivative, partial derivative of f with respect to x? So that we can equate this to our m and then solve for our g of x here. Since our new m is this one here, we'll equate this expression here to our found fx here by taking the derivative of this solved f of xy with respect to x. Well, these red ones will equate this so that we'll find the value of our g of x and then plug that into our solution f of x, y. So next step, we'll try to find our g of x. So equating, we have g prime of x is equal to x squared minus 3 over x plus 1 cubed, because we can cancel these out here because they are just the same. And to find our g of x, we integrate g prime of x, but we need to decompose this expression here, or g prime of x, into partial fraction. So meaning this form here, to change this and to decompose this into partial fraction, then multiplying x plus 1 to the 3 to both sides of the equation, and then we have arrived with this, and then rearranging to make this right hand side look like the left hand side, and then equate the coefficients of x squared, x, and the constant. So the coefficient of x squared here is 1. The coefficient of x squared here is a. That's why we have a is equal to 1. The coefficient here of x is 0. Coefficient of x here is 2a plus b. That's why we have b is equal to negative 2a and negative 2, because negative 2 times 1 is negative 2. And our constant negative 3 is equal to a plus b plus c. And finding c, we have is equal to negative 2. And we already decomposed this g prime of x into partial fraction. That's why we can find now its integral. The integral of g prime of x is g of x. Now, it's up to you to study how did I do the integration, but the final answer for our g of x is this: ln of x plus 1 plus 2 over x plus 1 plus 1 over x plus 1 squared plus c. And let's plug that into our found f of xy, our solution. And this is it. This is our solution, and let's equate that to c, and let's find the value of c by using this initial condition here: y of 0 is equal to 1. Change all the values of y to 1 and change all the value of 0 x to 0 to find our c. We have it here, we plug that in, and we can find that our c is equal to 5 over 2. Then subtracting 5 over 2 to both sides of the equation, and then equating that to c, we have now our final answer. And that's all. We can check that also that this is right. Here, our answer, because here, we can check that, and I think it's right, and that's all.